Okay, so on this screencast, we're going to talk about halogenoalkanes. These typically undergo nucleophilic substitution. Where the halogen is going to be replaced by a nucleophile, which is a species that is electron deficient. Nope, it's electron rich species. So it's looking for positive charges. It typically is going to replace the halogen in that halogenoalkane. These undergo heterolytic fission. And this is where the two electrons go to one species. We have to know about Sn1 mechanism and an Sn2. This is unimolecular and has more to do with the kinetics. So the rate is only dependent on the halogenoalkane. Sn2 is bimolecular, where the rate is dependent both on the halogenoalkane and the nucleophile. For example, something like hydroxide. Remember, you do need to know the mechanisms for these two, and we'll do those in just a moment. Generally speaking, if you're asked to compare rates, the rate of a tertiary halogenoalkane is typically going to be faster than a secondary, which is typically going to be faster than a primary. Speaking about mechanisms, saying Sn1 is faster than a combination of Sn1 and Sn2, which is faster than just an Sn2, which happens primarily with a primary. Halogenoalkane with a iodine is generally faster than one with a bromine, which is generally faster than a chlorine, generally faster than a fluorine, and this has to do because of the strength of the bond. The weakest bond is going to be fastest. And this takes priority over any polarity. Okay. Hydroxide nucleophile. Hydroxide nucleophile. Oh, geez. At least I didn't start writing yet. All right. Hydroxide nucleophile is going to have a faster rate than something like water, and it has to do with just being more electron deficient, more highly attracted to the nucleus. Okay. Halogenoalkane. If I got a new pen. Halogenoalkane. Halogenoalkane. If I put that in a solution of warm aqueous sodium hydroxide, the aqueous is the key part, I'm going to make an alcohol. If I put a halogenoalkane halogenoalkane in a concentrated solution of NH3 at high pressure, I'm going to make the amine. If I put a halogenoalkane in a solution containing the cyanide ion and I run that with a reflux in ethanol, I'm going to make a nitrile. The important thing about this is that it adds a carbon to the chain. Okay. So let's take a look at a primary halogenoalkane. Reacting with sodium hydroxide in a warm aqueous environment. Okay. When you're asked to show the mechanism, remember this is a primary alcohol, so it's going to be an Sn2. We're going to see that this pair of electrons goes to the carbon, and it's going to form the intermediate. So the unstable intermediate, and then the next step will be the chloro. The pen's not working well for me. Okay, I'll pick it up from here. So you'll end up with the primary alcohol and the chloride ion. Contrasting this to the reaction that occurs if I have the tertiary halogenoalkane. If I put this in warm aqueous sodium hydroxide, first thing that's going to happen is this pair of electrons is going to go to the bromide. I'm going to end up with the carbocation that shows stability because of the inductive effects of these alkyl groups kind of donating electrons to stabilize that carbocation. Then in that solution, the second step of this is for this pair of electrons to be attracted to and bond with that carbon, making a tertiary alcohol. And that would be the Sn1 carbocation. And this being the slow step is forming this bond electrons, leaving with the bromide group to form that carbocation. Then the last kind of reaction that we have to talk about. So I'm going to talk about the E1 mechanism. So I would have, say, a halogenoalkane in a warm alcoholic sodium hydroxide solution. First thing that's going to happen is I'm going to have that bromine, this bond, those two electrons going to the bromine. It's going to form the bromide ion. This bromide ion is going to go to this hydrogen. This bond is going to go between these two carbons. I'm going to form the alkene. And hydrogen bromine. That would be the E1. Oh, all right, so let's talk about the E2 mechanism. Okay, let's talk about the E2 mechanism. And this is kind of more of a concerted mechanism. I'm going to have these two carbons, other things attached to it. I'm going to have something that is the leaving group, say like that. This is a hydrogen. I'm going to have some nucleophile here. This nucleophile is going to give the electron pair to here. This pair of electrons is going to move in to form that double bond, and this is going to leave to go with the bromine. So at the end, I'm going to have like BHR, a alkene, and the bromide ion. You might have a different leaving group here. This might be water, hydroxide, but the idea is that this movement happens all as a concerted kind of one step. That kind of ends the discussion on halogenal alkanes. Hopefully this was helpful.